I guess hope all of us are doing great. In our discussion today, we're going to look at the quantum mechanical model. And this is one of the models that was proposed by a number of scientists and backed by experimental evidence to show that basically electrons behave as waves and particles at the same time. So in this case, we're going to look at a historical context of this particular case for the quantum mechanical model, and try to appreciate works of various scientists who came up with the model so that it gives us a clue on the present understanding of basically what an atom looks like. And we are also going to look at ways in which we can be able to describe various formulae that we may come across, especially on the issue of uncertainty and other areas that we are going to mention. So without further ado, thank you and welcome. So as I've said, our topic for discussion today is basically trying to look at the historical context of this development of the aspect of a quantum mechanical model of an atom. And we're going to look at works of a few scientists. Of course, there are various other areas which are going to work in collaboration with other topics to come up with the broader concept of quantum mechanics. But we're going to look at these specific areas, particularly in three areas of contributions which came up with the concept of the quantum mechanical model. Later on, then this is going to open for us a window of trying to discuss the concept of quantum numbers, which are going to describe different energy levels and of course number of electrons and various rules like the Aufbau principle, etc., which are going to assist us in describing the electronic configurations of various atoms. So in this case, for the quantum mechanical model, if we try to give it a historical context, we said that this one stems from the work of various scientists, sorry for that, who of course described a particular aspect of the phenomena that was being observed, and through experiments they tried to discard some of the evidence, or rather some of the arguments that have been advanced by some previous scientists concerning an atom. So the work of Max Planck, of course, gave an insight into how we can be able to describe energy of these particles. And of course, this particular particle is referred to as a photon, which basically implied a packet of light. So this is from the electromagnetic waves that we had looked into, whereby an argument had been made that basically an electron behaves as a wave-particle duality behavior. So wave-particle duality that was backed by various experiments. And for example, I can mention a few experiments of a double slit experiment that was performed by Young, and it confirmed over the waves behaving as particles. And then there was an experiment that was done by, this is a photoelectric effect that was described by Albert Einstein. This is a photoelectric effect by Albert Einstein. And then, of course, there was an experiment that was performed by Arthur Compton. That is the Compton effect, that also used to describe particles which are behaving as waves or having the aspect of momentum. And then we are going to see also the aspect of the black body radiation, which of course gave the concept of a quantum or a quanta, which we're going to see being described by, of course, Max Planck. So this, in collaboration with other topics from various areas that we're going to see, are going to give us a clue on how we can be able to pack up the concept of a quantum mechanical model of an electron. So in this case, of course, apart from other works of scientists, we are going to look at the various, particularly three areas that are going to give us a formula that is going to compound on the concept of the quantum mechanical model. So the first one that we're going to look at in this particular case, by giving an historical context, we're going to look at the work of Louis de Broglie, whereby Louis de Broglie argued that of course electrons behave or exhibit what we call a wave particle, that electrons exhibit a wave particle behavior, and therefore he gave a formula that was used to describe the wavelength of these particular wave particles as h over p. B represents the momentum, which is a product of mass and velocity from classical mechanics, and this is known as the Planck's constant. Therefore, from Redi-Broglie's argument, we're getting this aspect of the quantum, or rather the electrons behaving as waves and particles at the same time, therefore giving the concept, or rather packing this argument that had been given earlier of the wave-particle duality. So the second one that we're going to look at is the work of this German physicist by the name Werner Heisenberg. Now, the work of Werner Heisenberg, basically Werner Heisenberg described this aspect of position and velocity of an electron, which he said that this one cannot be pinpointed, or rather particularly one cannot pinpoint the velocity and position of a particle, such as an electron, at the same time. So therefore he came up with the Heisenberg's uncertainty principle, which states that the product of the uncertainty in position and the uncertainty in the velocity of a particle is equals or greater than h over 4 pi m. Of course, pi is a constant, and this is the mass of that particular particle. So therefore, in summary, apart from the de Broglie's lambda h over p, Werner Heisenberg came up with the Heisenberg's uncertainty principle, which states that one cannot pinpoint the position and the velocity of a particle, such as an electron, at the same time. Therefore, came up with the Heisenberg's uncertainty principle. So therefore, from his argument, it's only logical for us to look at an electron as a wave, contrary to us looking at it as a particle. So the third one that we're going to look at is the work of Erwin Schrödinger. Of course, I've done this one in one of our videos where I tried to derive the concept of a time-independent Schrödinger equation. So I'm going to put a link of that video in the description box so that we can just have a look at it. So this is a Schrödinger. So the work of Erwin Schrödinger provided a broader way in which we are going to redefine the wave-particle theory that, of course, was proposed by Louis de Broglie. So in this case, we're also going to look at in a slight historical context, in this case, of what had been done, especially that provide a basis for Erwin Schrödinger's argument. So the wave mechanics that had provided a basis for wave mechanics, of course, that we had mentioned, provide a basis for all the theories, which of course are going to entail the concept of electronic structure. So they form a basis for all theories which are going to explain the concept of electronic structure, and so also predicts what we refer to as quantized energy levels, and thus this provide a basis for us for the concept of a quantum chemistry. So in a sense, this is trying to explain the fact that basically wave mechanics that it describes the aspect of, or rather all theories of electronic structure forms a basis for the broader branch of quantum chemistry. So we're going to see that Erwin Schrödinger, of course, was the first scientist to successfully apply the wave nature of matter to explain the electronic structure by suggesting that electrons waves give different forms and patterns, which are known as orbitals. Of course, we're going to see that we had done a definition for this particular term that I'm referring to as orbital, and said that an orbital is a volume in space within which an electron with a particular energy is likely to be found. And we're going to see later that we have different types of orbitals that we are going to discuss about. But of essence for us is to try and figure out, since we have already mentioned on de Broglie's equation and uncertainty principle, so it will be okay for us to also try to give a figurative illustration of Schrödinger's equation in summary, and how it described this particular concept of orbitals. So therefore this one is just the formula that de Broglie, the Louis Schrödinger had given for the description of the energies of these particular electrons or particles. And we are going to see that also this formula is a compounded one that it describes also the position of these particular particles, which are wave-like in nature. So these symbols I've already explained on what they stand for in the video of the deriving the Schrodinger's equation for time-independent version 1. So I'm going to put a link in the description box so that we can be able to just go and have a check on what they basically imply. But from this case, I can just give a summary. This particular symbol, this is a wave function. A wave function, of course, that is going to be used in this particular formula to describe amplitude of that particular particle. We have done anatomy of a wave, so I presume that we understand all these terms that we're trying to put in this case. So m in this case refers to the mass of this particular particle that is under discussion, and then this particular set of this equation for z describes the potential energy the particle has at each position. So potential energy. We have decided that the energy of a particle, of course, it contains internal energy, potential energy, and kinetic energy. So therefore, whenever we are talking about the potential energy the particle has at each position, therefore, I presume that we're going to understand that. So in summary, this gives the description of a Schrodinger's equation. Of course, we're going to just have an elaboration of what these other details entail, especially in that particular video that I'm going to put a link in the description box. So lastly, we're going to look at this aspect of the quantum mechanical model, trying to give these particular volumes in space that have a probability of finding an electron that I've referred to as orbitals. So therefore, we're going to look at different shapes of orbitals in summary before we proceed to look at various quantum numbers, which of course are going to assist us in describing the electronic setup or configuration of various atoms, which are going to come later. So in this case, I'm going to have a few models of this structure. And therefore, as I've said in summary, the quantum mechanical model is going to describe various aspects of these locations of electrons in an atom by describing what we refer to as the principal energy. And in this sense, the principal energy is going to be given generally in our discussion by the letter n. And in this case, the principal energy basically is going to refer to the size and energy of atomic orbitals. It's going to give the size and energy of atomic orbitals. And then next, the quantum mechanical model is going to describe what we call energy sublevels. Energy sublevels. And this basically are going to be what we define as orbital shapes. So therefore, we're going to have S, B, D, and F as various ranges of orbitals that we're going to look into. And then next, the quantum mechanical model is going to describe the orbital, which I've mentioned as various volumes in space where there's a possibility of finding electrons, and basically which are sublevels from what we have mentioned above. So therefore, lastly, we're going to see the quantum mechanical model trying to describe what we refer to as spin, which basically say we're going to see that the orientation of electrons in an energy level is going to depend on their moment. So therefore, this is going to generate electrical field. This is going to give you this aspect of the spin. So now, from the of-course principle and the arrangement of this particular kind of electrons, then therefore we're going to see a deeper elaboration on what this concept of a spin refers to. So I'm just going to give a short summary of arrangement, or rather the figurative illustration of various orbitals. So for instance, I've said we have S, P, D, and F orbitals. Now for S, we can have one S orbital, which of course is spherical. Mine might not be just elaborate but it's frequent. Then we have what we call for p orbitals. If we have this particular illustration for three-dimensional space for z, x, and y, then we can have an orbital along the y-axis that is going to be described as py orbital. So similarly, you can have a pz orbital along this one, or a px orbital along that specific part. And then next we can have one example for the d orbitals. So suppose we have still this Cartesian coordinates x, y, and z. Now this is going to lie along the xy plane. So therefore this is going to be appearing like this along those axes. And then we shall have this one lying along the xy plane. So this is going to be referred to as the dxy orbital. And then lastly, that we're going to have an orbital for f, which is going to lie in the spaces between those three-dimensional axes for x, y, and z. So suppose we have x, y, z, and we can have an orbital for this f, which is having like close two branches at this particular, in all the spaces that are found in this particular place. So we're going to have this occupying that space. So this one is going to be f, x, y, z, of course, orbitals represented as such. So in our next discussion, we're going to look at quantum numbers and how we can be able to note whether, or rather try to figure out the number of electrons which are going to be occupied in these various orbitals for s, p, d, and f of various energy levels and the sub-energies that we have talked about. So I'd like to invite us in our next video where we're going to look deeper into the concept of Aufbau's principle and other rules which are going to assist us in refining the concept of electronic configuration. So that it is for now. I like guys to encourage us to go to YouTube and search Ernest Sciences and Mathematics TV channel, and welcome on board so that we can have a broader based discussion. So that it is for today, guys. Thanks. God bless you. Bye.